Hi everyone, I am Yunhe. I come from Institute of Information Engineering, Chinese Academy of Sciences. In our research, we proposed a general framework to verify the data integrated in the cloud using SGX. Nowadays, more and more people or companies choose to store their data on the cloud storage service. Cloud storage service is so popular because of some attractive features. For example, pay-as-you-go, electricity, cost saving, etc. And there are many popular cloud storage services for us to store our data, such as Google Drive, OneDrive, Dropbox, and so on. Then come to one question: is there any issue in such data outsourcing model? When we store our data on the remote cloud server, we have to face some issues. For example, data disclosure, data privacy, the data integrity, data corruption, or data loss. In our research, we focus on the second problem. How do we verify the integrity of the data stored on the remote cloud server? To verify the integrity of the data stored on the remote server, many PDP schemes, which based on cryptography, were proposed in the past years. The PDP is the abbreviation of probable data position. How we simply divide the PDP schemes into two types. The first type is public audit. As shown in this figure, for this type, the verifier is the TPA, that is the third-party auditor. The TPA sends challenges to the cloud on behalf of the users, and then it verifies the proofs generated by the cloud. Finally, the TPA returns the verification results to the cloud. However, there are two security issues about the first type PDP schemes. The first issue is the honest but curious TPA may potentially learn the user's data. The second issue is the TPA may collaborate with the cloud server to deceive the users. That is the closing attack. The second type PDP schemes is private auditing. The verifier is the data owner. The data owner sends challenges to the cloud and they verify the proofs by themselves. But there is also one limitation for the second type PDP schemes. The limitation is the client bears the computation overhead of performing verification operations and challenging. Besides, all of the PDP schemes have one common limitation. There exists a very high communication overhead between the TPA and the cloud server, or between the clients and the cloud server. So in our work, we show that we can use Intel SGX to overcome these limitations of the PDP schemes. Intel SGX is a hardware feature of the Intel processor. It enables an isolated execution environment named enclave within a program's address space. Even if the privileged software, for example, the operating system, cannot violate the protection of the Intel SGX. So the security features of Intel SGX can overcome these limitations of the PDP schemes perfectly. Firstly, SGX can replace both the TPA and the client, so it is compatible with all the PDP schemes. The second, SGX can eliminate the security issues introduced by the TPA. The SGX protects verifier race on the remote server, so the cloud server bears the computation overhead. The verifier protected by the SGX is collected with the cloud storage service, so the communication overhead between the verifier and the cloud storage service is just only inter-process communication, rather than network communication. This figure shows the architecture of EnclavePDP. Generally, there are 5 major functionalities in a PDP schemes: keychain, tag, challenging, proof, and verifier. The keychain and tag are running on the client side, so the security of these two functionality depends on the client. Proof is conducted by the prover, that is the cloud storage server. Challenge and verify operations are performed by either the client or the TPA. So in our solution, we only place these security-sensitive operations and the security-sensitive data in the enclave. For EnclavePDP, we press challenge and verify operations inside the enclave, and we store the private keys in the enclave. The EnclavePDP consists of 5 modules. The request handler runs outside of the enclave. It is responsible for loading enclave and forwarding message among other modules. The challenger runs inside the enclave. Its duty is generating challenges for the PDP schemes. Similarly, the verifier module inside the enclave is responsible for verifying proofs generated by the prover. Prover is a regular application. It generates proofs of the data position on behalf of the cloud storage service. The private key loader is designed to securely load the private keys into the enclave. The workflow includes initialization and verification phase. In the initialization phase, the client generates keys, including public keys and private keys. The client uses these keys and the data to generate text. The client performs remote attestation to verify the EnclavePDP's integrity and then creates a secure chain. This secure channel is used to upload private keys and other secret data. The EnclavePDP encrypts this secret data and stores them to the disk. The data, the tag, and the public keys will be uploaded to the cloud server. In the verification phase, the client submits a PDP request. Then the challenger generates a challenge based on this request. Challenges will be forwarded to the prover. The prover generates a proof for this challenge. Verifies the proofs and then returns a verification response to. In our prototype of EnclavePDP, we choose 10 PDP schemes and ported them into enclave. 3 crypto libraries, OpenSSL, GMP, PBC, or tailored and ported into enclave. For ease of deployment, EnclavePDP exposed high-level interfaces for users on the cloud storage service to submit PDP requests. We have deployed EnclavePDP on FastDefense, our open-source distributed file system. This integration less than 300 lines of C code. We also integrated EnclavePDP with Amazon S3. This integration about 17 lines of C code. To protect the enclave binary integrity, we use Intel SGX PCI technology to encrypt the enclave object file at the boot time and decrypt it at the enclave load time. In this section, I will show the performance of EnclavePDP. There are 3 concerns about using Intel SGX in our framework. The first is compatibility. To overcome this concern, we have turned and ported 3 crypto libraries required by the PDP schemes into the enclave. The second concern is memory usage. The Intel SGX only provides 128 megabytes for applications, so we trimmed the unnecessary modules in the crypto libraries and only pressed the critical parties of the PDP schemes in the enclave. The second concern, runtime performance. Switching control between the enclave and the non-enclave will impose higher runtime overhead. To answer the above concerns, we did the following agile evaluation. The first, we measured the code base in the enclave, that is the TCBCs. The second, we evaluated the overhead introduced by the Intel SGX when performing the challenging and verify operations inside the enclave. The third, we measured the response time and throughput of the 10 native PDP and their enclave-enabled version. To make a reasonable evaluation, we have deployed the EnclavePDP and FastDefense on Microsoft Azure Confidential Computing virtual machines. As shown in this table, the security-sensitive length of code of native PDP varies from 7% to 33%. The security-sensitive lengths of code after porting them into enclave varies from 80% to 36%. Such increase merely result from extra functionalities, for example, private key rolling, changing backup disjoint, decrypting security system data, and so on. We also measure those three enclave supported libraries code base. In general, the memory footprint of the code base in the enclave is reasonable. This figure shows the time of generating challenges for both enclave-enabled and native PDP schemes with different fail sets. From this figure, we got our first observation. The overhead of the challenge operation is not proportional to the security system length of code. PDP schemes in the same category introduce similar overhead. Enclave-enabled challenge operation time is still in the scale of microsecond, which should have a little impact on practical application. This figure shows the time of execution the verify operation for both enclave-enabled and native PDP schemes with different fail sizes. Our second observation, RSA-based schemes an order of magnitude slower than symmetric-based schemes. Because the RSA-based module exponential operations are complicated and expensive. BS-based schemes are another order of magnitude slower, probably due to the inherent drawback of the complicated and slow computation of BS signatures. Our third observation, running the verify operations instead of the enclave introduces less overhead compared with the challenge operations, because the challenge operation is relatively lightweight compared with the verify operation in terms of computation. However, the following experiments will demonstrate that such microsecond range or millisecond range overhead makes acceptable or even negligible impact on the throughput for the practical deployment. We have measured the response time and the throughput of the 10 PDP schemes when verify on big file and a small file. Our fourth observation, the impact incurred by the EnclavePDP to the entire response time is acceptable for practical deployment. In fact, the throughput and the response time of the EnclavePDP is still in the same order of magnitude of the native PDP. Our fifth observation, to support dynamic audit, the performance of PDP schemes like FlexPDP downgrades significantly due to the expense of building and managing memory-consuming data structure, like, for example, Flex. We also measured the proportion of challenge verify time to the total response time when only launch one thread to issue a PDP request each time. Our last observation, the verification time of the BS-based schemes accounts for much more proportion than that of other schemes, which will explain why running BS-based schemes in the enclave introduce more overhead compared with other PDP schemes. For most of the PDP schemes, the runtime of the challenge operation and the verify operation accounts for a quite small proportion of the total response time, which is in line with the fact that although per challenge or verify operation introduce relatively high overhead, the impact to the per PDP request is almost negligible. To sum up, we proposed and implemented a general framework that can securely verify the integrity of the outsourced data using SGX, which eliminates the dependency on NetPA. 3 crypto libraries are tailored and ported into Enclave to support both the existing and new PDP schemes, and 10 PDP schemes are ported into Enclave with reasonable effort. We performed a comprehensive evaluation of the EnclavePDP by deploying it on a real cloud storage service. Our evaluation results eliminate the performance concern of running PDP schemes in the interest. That's all. Thank you for your attention.